Unit 2.8 deals with what is called electronegativity. Now, electronegativity, kind of a big word, but pretty easy, hopefully, to understand. Okay, electronegativity, now that we've learned how to draw Lewis electron dot diagrams, okay, we've got this bond right here. And let's say we've got that bond, and then we've got a bond between, say, carbon and fluorine. Okay, something like that, okay? And we know that those bonds are different because one of them has a carbon-fluorine bond, one is a fluorine-fluorine bond, okay? Electronegativity is the ability of an atom, so it's the ability of an atom to attract electrons to itself in a bond. Okay, so it's really saying which of these two atoms, fluorine or carbon, can attract those electrons to itself more than the other one can. Okay, the greater the electronegativity, the more that atom can attract electrons to itself. So in this case, we haven't learned why, but fluorine does have a greater electronegativity than carbon does. So what that means is it means that these two electrons that are right there in that bond between carbon and fluorine are more attracted to the fluorine than they are to the carbon. In this case, because with the fluorine, because it's the same atom on both sides, neither one of them has a greater electronegativity than the other. So we can say that those electrons are shared equally between the two fluorine atoms. Whereas over here on our right-hand side, in this example, because fluorine is more electronegative than carbon, we would say that yes, they're still sharing in the electrons, but because fluorine has a greater electronegativity, those electrons are closer to the fluorine side than they are to the carbon side. Okay, so it has to be in a bond. Okay, electronegativity has nothing to do with these electrons out here. Electronegativity only deals with those electrons that are in that form those bonds between the two different atoms. Okay, and if you'll notice down here, here's a table of electronegativities. You'll notice that it stops before the end of the periodic table. Like next to fluorine, where's neon? Next to chlorine, where's argon? Where are the noble gases? You'll notice that the noble gases aren't even there because they don't form bonds. Okay, in general, sometimes you can force them to make bonds, but in general, noble gases don't form bonds, and since electronegativity only deals with the electrons in the bond, we don't even talk about, they don't even put the noble gases on the table when they're talking about electronegativity. Okay? Now, you'll notice the trend here. Again, forget about the D subshell altogether. We're simply looking at the S and the P subshells. Notice there is a trend similar to ionization energy, similar to atomic and ionic radius, that as you go across the periodic table, so from left to right across the periodic table, the ionization energy, the electronegativity increases, okay? And why does it do that? The same reason that the ionization energy goes up and the same reason that atoms get smaller, the atomic radius decreases. Because, again, you're increasing the number of protons, but you're staying within the same valence shell. The valence electrons are all in the second shell, they're all in the third shell, etc. Okay, so the number of core electrons, remember typically we call those the inner shell. The inner shell electrons stay the same. You're not adding any more electron shells to that atom. Okay, so an increase in the number of protons, but the valence electrons are staying in the same shell. So the biggest factor there is that number of protons. More protons means more attraction. So since there's more attraction, that means that that atom is going to be able to pull those electrons with more force than the other atom's going to. Okay, and then as you go down the periodic table, what happens? Same thing with ionization energy, it goes down. So from top to bottom, electronegativity decreases because, again, the number of electron shells that are farther away from the nucleus also increases. You're adding more electron shells, that puts more distance between the nucleus and those valence electrons. Okay, and that decreases the attraction to the nucleus, So electronegativity goes down. Okay? So let's take a look at some questions here. So this is the exact same pattern as ionization energy, same pattern as atomic radius. We now know there's three things that happen as you go across the periodic table. One, ionization energy increases. Number two, atomic radius, the size, right? The atomic radius decreases. And number three, the electronegativity increases. All three of those things happen as you go from left to right. And the reason why all three of those things happen is exactly the same. Because the number of protons increases, so the attraction to the nucleus is stronger, yet the valence electrons are all in the same shell, so you're not adding any distance to that between the nucleus and the valence electrons. Okay, as you go down the periodic table, three things happen. Okay, I'm going to abbreviate here. Ionization energy, what does it do? It decreases. Okay, atomic radius increases, so atoms get bigger, and electronegativity also decreases. Okay, so ionization energy, atomic radius, and electronegativity. Okay, and again, why does that happen? Why does the ionization energy and electronegativity go down, but the radius get bigger? Because you're adding more electron shells. Adding more electron shells that are farther away from the nucleus, that has more of those inner shell electrons blocking the attractive force of the nucleus. Atoms absolutely get bigger, and it's easier to take electrons away from them, and the attraction to the nucleus isn't as strong, so all three of those things happen. Okay, example one, which of the following elements is more electronegative, boron or fluorine? Well, you can look up here and answer it. Okay, clearly fluorine. Okay, but really it's being able to explain why. Why is fluorine more electronegative than boron? Because their valence electrons are in the same shell, but fluorine has more protons, so there's a greater attraction to the nucleus. So in a bond between boron and fluorine, for example, this is a chemical compound right here, BF3, it means that these electrons right here in this bond are more attracted to the fluorine side than they are to boron. Okay, so in all three of these cases, you've got electrons in the bond that are more attracted to the fluorine than they are to the boron. And that's going to become important here in one of our later videos. Okay, what's more electronegative, fluorine or iodine? So fluorine versus iodine, clearly fluorine. What's the most electronegative element on the periodic table? Look at it. It's right there in front of you. It's fluorine. Okay, fluorine is the most electronegative element there is. Okay, how about aluminum or carbon? Again, this one you can kind of just look. Aluminum's 1.5, carbon's 2.5, certainly carbon. Okay, and then hydrogen, 2.1. Phosphorus, hey, what do you know? 2.1, two of them that are exactly the same. So hydrogen's farther to the left, but phosphorus is farther down. I wouldn't expect you to know that, okay? They actually are equal to each other. And then what's the most electronegative one on the periodic table is fluorine. Okay, and again, the key here is not necessarily can you identify, like on a test or something like that, I'm going to tell you which one's more electronegative. You're just going to have to tell me why. Okay, I'm going to say, why is fluorine more electronegative than iodine? Okay, and you'll say, well, because iodine has more electron shells that are further away from the nucleus, and that decrease, and lots of inner shell electrons blocking that attractive force. Okay, where fluorine doesn't. So when you go across the periodic table, what's more important is the number of protons. Since the valence electrons are all going into the same shell, when you go across the periodic table, the more important thing to discuss is protons. When you go down the periodic table, what's more important? Not the protons. Because if you notice, the protons are increasing, but I never even mention them because the more important part when you're going down the periodic table is the number of electron shells, which means the distance, okay? The distance from the nucleus to those valence electrons is much farther as you add more electron shells to that. Okay, and then we will talk about how do we use that. That's just the introduction there to electronegativity. In our next video, we're going to talk about, okay, how does that apply? How do we use that in chemistry? Because electronegativity is really, really important, and we'll get to that in our next video.